So, energy transfer. We're looking at how energy is transferred by flow of electric charge and how it's related to potential difference. But before we go any further, it's time to review some of the things that you've done in the previous lessons. So, answer these questions. I'll read them out to you, pause, write down the answers, then unpause and check how you have done. What are the units for the following quantities? Energy, power, charge, potential difference, and current. What are the names of the three types of wire in a plug? What are the different types of fuses you can use? Which fuse would you put in a washing machine? Which would you put in a lamp? And what is inside a fuse? What happens when the current gets too high? Pause, write down your answers, and then unpause and check. Okay, so what are the units for the following quantities? Check my pen works. Energy is measured in joules. Power. Power is measured in watts. Charge is coulombs. Potential difference is volts. And current is amps. What are the names for three wires in a plug? You have neutral, live, and earth. What are the different types of fuses you can use? There's 3 amps, 5 amps, and 13 amps. Someone at my door. I have to wait a second. Which of these fuses would you put in a washing machine? Washing machines will take the highest because they do heating and they have a motor. What would you put in a lamp? Lamp, you do the lowest. There's no heating, not intentionally, and there is no moving parts. Inside a fuse, what is it? What is inside a fuse? And what happens when the current gets too high? Inside a fuse is just a wire, whoop, like this. So it looks like that. And you've got the casing. And what happens when the current gets too high? When the current gets too high, the wire just snaps, breaking the circuit. Well, it doesn't snap, it melts, and that breaks the circuit, meaning no more electric current to your device. So, you've learned a lot of equations so far. Now, you probably not learned all of these, but actually you have. Some of them are just different ones. So this one, let's remind ourselves. Q equals IT, charge is current times time. This one, potential difference or voltage, I'm just being lazy. Volts is current times resistance. This one, power is energy over time. This one is power is also power. Current, we know that one, times voltage. And actually, if you take this one and combine them, P equals IV, but we know V equals IR. So P equals I, IR, which is the same as P equals I squared R. This is just this one rearranged. E, energy, is power times time. But also, energy is Q, which is charge, times volt. And this one actually is probably the important one of the important ones we need today. E is QV, or if you rearrange it, you can have E Q V. We put it into a little triangle. So 1 volt is energy over charge. 1 volt is equal to 1 joule per coulomb. 1 volt is 1 joule per coulomb. And we're looking at energy used in the circuit. So if something uses 1 volt, is using up 1 joule for every coulomb of charge that is moving around that circuit. But let's put that together into the next thing. Chance for you to practice one of the equations. So here we have a different appliance. So P, I, V. Okay, so this links back to that question in the starter. What fuse would you use for the different things? So power is P, current is I, and voltage is V. Now, if all of these things are plugged into the mains, as in they're plugged into the wall socket in your house, they'll get 230 volts. 230 volts. If I put this like this, P, I, V, as a little triangle. If I want to work out what the current is P divided by V is equal to current. So this one, power, 60 watts, divided by V, well, every single one of these is going to be divided by 230. So 60 divided by 230, put that through the calculator, is 0.26 amps. For a low power device, you only need a small current. For a big device, you'll need a larger current. So that makes sense. So all you have to do is write down the sum for question 1, or write down the sum 60 divided by 230 equals 0.26. Do the same for a mobile phone charger, a kettle, a hairdryer, a vacuum cleaner, a TV, and a PlayStation. Pause, finish that, unpause when you're done. Done? Splendid. So when we're talking about energy transfer in a circuit, here we have a bulb and a variable resistor in series. Now, it's 12 volts. What was the rule for potential difference or voltage in series? In series, you must use it up as you go around the circuit, but it's shared. So 12 volts has to be shared between the bulb and the variable resistor. So maybe the bulb takes 10 and the variable resistor takes 2, or they both take 6. But whatever you go through the voltage, through the bulb, and whatever you have through the variable resistor must add up to 12. And we know, I gave you that equation earlier. So, for example, if this reads 2 volts, oh no, it says 10, sorry. This says 10 volts. How much is going through the potential difference? How much is going through the other one? 2 volts. Excellent. Oh, this is 2. So 2 volts is equal to E over Q. Well, for every coulomb, 2 volts means you get 2 joules. So let me just read it so I don't say it the wrong way. So each coulomb of charge leaves the battery with 12 joules. If the voltmeter reads 10 volts, this means 10 joules of every coulomb goes to the bulb, which is transferred as light and heat, and 2 goes to the variable resistor, which is transferred as heat. So they use their energy up as they go around the circuit. Now, the energy they get from the battery, this is a battery, so what type of energy do we have in a battery? It's chemical. But what does a battery do when what type of energy does it transfer into? Electrical energy. So chemical energy turns into electrical energy. Then it goes into the bulb. And that electrical energy in the bulb goes as light and heat. And then when we go to the variable resistor doesn't do anything apart from resist, so it's lost as heat. So that's how the energy is transferred in the circuit. So chemical energy from the battery turns into electrical energy that flows around the circuit, and the electrical energy in the bulb becomes light and heat, and in the resistor just becomes heat. So let's have a go. What is a useful energy output for each of the following appliances? Complete the sentences below. An electric fan transfers electrical energy into, well, what is a fan's job? Fan's job is to blow air around the room. But how does it do it? It does it by spinning. So and what is spinning or movement energy? Begins with a K. Kinetic, well done. A lamp transfers electrical energy to something as useful energy. We mentioned before, lamps give off heat. If you touch a lamp, you'll notice they're hot. But that's not what you want them for. What do you want them for? You want them for light energy. An electric heater transfers electric energy to... What's the job of a heater? Thermal energy. So, underneath different appliances in your house, you'll have these things. Lift up a kettle. This is from a kettle. And it'll tell you the power rating. Or if it doesn't tell you the power rating, it'll tell you how to work out the power rating. So this one works at between 2,520 to 3,000 watts. It runs between 220 and 240 volts. It also runs on 50 to 60 hertz. That means it's alternating current. But these two will allow us to work out for many things, because we know P equals IV. So we now know, P, we know I, we know V, and we don't know I. So we know P is, at the most, it's 3,000, and V is, in the UK, it's 230. So if we do 3,000 divided by 230, that gives us 13 amps, which is quite a lot, high current. So the power rating for that device is between 2,500 to 3,000 watts. So here's a chance for you to test some of the things. If you're not super confident with this, maybe you should write the whole thing down. But in reality, all you need to do is write down the answers. So fill in the spaces below with the words. The words are current, large, energy, second, potential difference, watts, and time. And I've written the numbers 2, 3, 4, 5, 6 along the side for a different. So you write the answer. So write down number 2. Power is the energy transferred by a device each and is measured in something or joules per second. A machine with a high power rating will transfer a something amount of energy each second. Power is calculated using the equation. Power is power something times something. For electrical devices, power can also be calculated using the equation. Power is something times something else. Okay, pause. Another question. Calculate the power rating of the following devices. A hairdryer, which converts 40,000 joules of electrical energy to heat energy and kinetic energy every minute. So we want power. The equation for power is energy divided by time. But do we want time as minutes? No, we don't. We need time as seconds. An electric iron, which converts 72,000 joules of electric energy in 10 minutes. It's giving you an energy. Don't forget to convert the time to seconds. A microwave uses a lot of energy and to defrost a chicken in half an hour. Don't forget to convert to seconds. Pause, do it. Here we have another chance for you to try the equation. P equals IV. Power is current, power, current, and potential difference. Can you copy the table? Fill in the missing values. And number 11, a television has a power rating of 160 watts. A light bulb has a power rating of 40 watts. And a dishwasher, power rating of 1,150 watts. Calculate the total energy transferred by all these appliances if they're used for a period of 4 hours over a day. Remember watts, so joule per second. How do you work out how many seconds there are in 4 hours? How many seconds are in a minute? 60 seconds in a minute. How many minutes in an hour? So that is how many seconds in 1 hour. Times by 4 hours, times by 4, tells you how many seconds in 4 hours. My head's in the way, as always. I gave you an example. Here is an example of another casing or sticker that you might find in an electrical appliance. 1,100 to 1,200 watts. Quite high power, not as high as a kettle. I don't know, maybe a toaster or microwave or something like that. Use the information to work out the minimum current, the maximum current, and the average time taken for the appliance to transfer 4 megajoules. What's mega? There we go. That was easy. Just some questions. That's all it is. Okay, you need to know those questions for the next lesson, because if you can't do those questions, everything becomes a lot trickier. So practice the questions. I believe in you. Good luck.